Good morning, everybody. Next program is determination of bus currents, bus power, and line flows for a specified bus system profile. So, as usual, this is coming under the post load flow calculations. Once the load flow analysis is done using either Gauss-Seidel, Newton-Raphson, or FDLF algorithm, these calculations will be carried out. In load flow analysis, you would have already found the voltage across various buses, current flowing through the various transmission lines, active and reactive power flowing through the transmission lines. These information you would have got. So using this information, further calculations will be done, and this particular program is based on that. So let us just have a look at the background concept and then go to the program. So here, let us see some formulas here. Please have a look at this network. It has bus 1 and bus 2. In between, there is a transmission line, and the transmission line is modeled using nominal pi model, and the series admittance of the line is Y12. Shunt admittance of the line is Y120 and Y210. These are the line charging admittances. It is named as Y120 because it is in the vicinity of bus 1, and Y210 as it is in the vicinity of bus 2. And I1 represents the current flowing from bus 1 end, I2 represents the current flowing from bus 2 end, and I10 is the line charging current, and I20 is also the charging current of the capacitor. I11 and I21 are the currents entering from either directions into the admittance. So here we have the first equation for current I1. So if I have to write the expression for current I1, I have to use KCL. So I1 will be equal to I11 plus I10. As you can see in the network, at this particular junction, we are applying KCL. So I1 will be equal to I11 plus I10. So we are interested in expressing I10 and I11 in terms of the voltage, corresponding voltage and line admittance, product of voltage and line admittance. So I11 will be V1 minus V2 into Y12, product of voltage and voltage in the sense potential difference and admittance, and the current I10 is given by V1 into Y12. Now we'll take the conjugate of I1. So we have V1 conjugate minus V2 conjugate into Y12 conjugate plus V1 conjugate Y120 conjugate. The power fed into the transmission line from bus 1 is denoted by S12, which is equal to this is nothing but the complex power, so it is a combination of or the active power as well as reactive power, so it will be P12 plus J Q12, and the complex power is also given by VI conjugate in general. So here it will be V1 into I12 conjugate. So V1 I retain as it is. In place of I12, I'm writing the expression. So in place of I12, I already have this I1 conjugate here. So same thing will be applicable. So V1 conjugate minus V2 conjugate Y12 conjugate plus V1 into V1 conjugate Y120 conjugate. So here in general we have called it as I1, that is same as I12 because we are considering the current flowing from bus 1 to bus 2 as I12. So your I1 is taken as I12 here. Then similarly we write down the expression for power fed from bus 2 into the line, that will be denoted by S21, which is equal to V2 into I2 conjugate. So V2 multiplied by V2 minus V1 Y12 plus V2 Y210 conjugate, similar to what we have done in the previous case. So S21 will be equal to V2 into V2 conjugate minus V1 conjugate Y12 conjugate plus V2 into V2 conjugate Y210 conjugate, very much similar to what we have done in the previous case. So the total power loss in the transmission line is given by algebraic sum of S12 and S21. So the total power at a particular bus is given by S11 plus S12. So now let us see the implementation of the same using the program. See, this is a direct implementation. We earlier have seen the formulas. We are just going to use represent the same in the standard format. First, we take VBus input, enter the bus voltages. See, voltage at various buses already we would have got from load flow studies. We are going to input the same. Then YBus is equal to input, enter the bus admittance matrix. Already YBus of the system will be known while solving load flow problem. That also will be taken as input. Then in order to find the size of the YBus matrix, we are going to use length instruction. So n is equal to length of YBus. So this n will determine the size of the YBus. Now we are defining a variable st, which is given by zeros of n comma n. That means we are going to initialize st, which is the total bus power, with zeros of size n cross n. So we'll be defining a n cross n matrix having all elements being zeros and call it as st. Now starts the loop for I varying from 1 to n. I is a variable which varies from 1 to total number of buses. N is total number of buses. N basically defines the size of your Y bus. So for I varying from 1 to n, for k also varying from 1 to n, if I is equal to k, continue. That means to say we are not interested in diagonal elements. If I becomes equal to k, obviously we'll be dealing with diagonal elements. We are not interested in them. Then it will just say continue. Else we are having these instructions. Else in the sense when I is not equal to k, we are referring to the off diagonal elements. Capital I of I comma k will be equal to minus y bus of I comma k into v bus of I minus v bus of k. See, here there is a catch. We are taking negative sign here. This is because whenever you are writing Y-bus matrix, the off diagonal elements, you take the negative of the admittance connected between the various buses. So if you want the actual admittance, since your input is Y-bus, already negation is taken. So you have to remove that negation. I am using a negative sign here. So Y-bus into V-bus of I minus V-bus of k. So this is nothing but V1 minus V2 into Y1k will be equal to IK, product of potential difference and admittance. That is what is being done here. Then I of Ki is equal to minus I of Ik. Current flowing from either sides is equal in magnitude but opposite in direction. So that is what is happening here. Then S of I of k is equal to V bus of I into conjugate of I of k. S is nothing but Vi conjugate, that is happening here. S of k of I is equal to V bus of k conjugate of I of k comma I. Here also it's the same. It is as good as S12 and S21. Then the transmission loss SL I comma of I comma k is equal to S of I comma k plus S of k comma I. S12 plus S21. Algebraic sum if you take, you will be getting the transmission loss. Then total power at the bus ST. T represents total. ST of I comma I is equal to ST of I comma I plus S of I comma k. This is how you get the total power at the bus. Then end instruction. After end, you have S bus. The power at the bus is given by ST of 1 comma 1 in the first row, ST of 2 comma 2 in the second row, ST of 3 comma 3 in the third row. So this will represent total power at all the buses. Then in order to find the bus currents, I bus is equal to conjugate of S bus dot divided by V bus. You know that S is equal to VI conjugate. So if you want I over there, you just go for S divided by V conjugate. That is what is happening here. Then finally we are interested in displaying the value of S bus and I bus. So this completes the program on determination of bus currents, bus power, line flows for a specified bus system profile. This ends experiment number 4.